Hi everyone. Today let's talk about session 2.1, the idea of limits, and session 2.2, definition of limits. Big idea. A limit is the number to which a sequence of ever better approximations converges. In this session, you will use secant line to approximate the tangent line at a given point on the graph of a function. In the limits that the secant points of the secant line approach the tangent points, the slope of the secant line approach the slope of the tangent line. One hard part about limits is finding a function that accurately describes the ever better approximations. In this session, however, the function will be given to us. So we just need to plug in numbers, put the numbers into the function and look at its graph to conjecture what the limit really is. Another hard part about limits is rigorously proving what the limit actually is. We will deal with that in session 2.3. Big skills. You should be able to use graphical and numerical evidence to conjecture the limits of a given function at a given point. So we have an example. Suppose we are driving on a straight highway. If we pass ma1200 at noon and ma1230 at 12:30 p.m., we travel 30 miles in a half hour. So what is our average velocity? Okay, average velocity is the distance traveled over the time traveled. So we have traveled 30 miles and within a 0.5 hour, right? Half an hour is 0.5 hour. So 30 divided by 0.5 is 60 miles per hour. So this is our average velocity. So even though our average speed is 60 miles per hour, but our instantaneous velocity, which is the speed indicated by the speedometer, varies from one moment to the next. Okay, so here let's look at example 1. A rock is launched vertically upward from the ground with a speed of 96 feet per second, neglecting air resistance. The position of the rock after t seconds can be described so we're given the function s of t equals negative 16t squared plus 96t. Okay, we want to find the average velocity between t is 1 second and t is 3 seconds. So here the function is given. Okay, so average velocity equals the distance travel over the time, right? What's the distance travel? Well, that is s of 3 minus s of 1 divided by 3 minus 1. But what is s of 3? Well, that means this is our function, s of t. We plug in t equals 3. So minus 16, 3 squared, which is 9. Plus 96 times 3 minus. So here, please don't forget the parentheses. So parentheses is like our baby. Super, super important. I know you haven't had a baby yet, but maybe your future baby, right? So it's so important. So don't forget your baby in the mall. Okay, so now we plug in 1 into the function s of t. So negative 16, 1 squared is 1. And 96, oops, sorry, I pressed something. 96 times 1 is 96. So in the bottom, we have 3 minus 1. So what is that? Well, let's see. We get minus 16 times 9 plus 96 times 3. When we want to get rid of the parentheses, we become plus 16 minus 96, right? 3 minus 1 is 2. Alright, so what do we get? We can plug this in our calculator, right? But if you can realize, well, this guy and this guy, we have a common factor, 16. So, if we factor out the 16, okay, actually we factor out minus 16, then we have 9 minus 1, because this is plus. When we factor out the minus, it becomes minus 1. And then this guy and this guy, we have the 96 as the common factor. So 96 and then 3 minus 1, right? So, okay, minus 16 times 9 minus 1 is 8, plus 96 times 2. So we can actually simplify the answer, right? So what is 16 times 8? 8 times 6, 48. 8 times 1 is 1. So 128. What is 2 times 96? 1, 2 times 6, 12. 2 times 9, 18. 192. Right, 192. 192 minus 128 is 4, and then 64, right? 64 over 2, which is 32. So this is what we can calculate without a calculator. But if you want, from this step, you can plug in your calculator, and then you get 32 feet per second directly. So this is the average velocity, right? And then next, how do we find the instantaneous velocity? Well, here, let me introduce a definition. A line joining 2 points on the curve is called a secant line. So you can see all of these green lines, they are secant lines. Okay? The slope of the secant line is, well, we know, how do we find the slope? Well, change of y over change of x, right? Oh, in this case, we have t and s. So change of s over change of t. This is the slope, right? So the slope of the secant line, change of s, is s of t1. So let's say this guy is t1. So this guy is t0 and this guy is t1. So this is s of t1 minus s of t0 over t1 minus t0. So this is the slope of the secant line, right? We need 2 points for the secant line. We need 2 points on the graph. Next, when the 2 points get closer to each other, the secant lines approach a unique line, which is called tangent line. So you can see this red line, it tangent to the curve at the point t0. Okay, so the slope of the secant line, because you can see when we let the second point getting close to the first point, the green lines actually converge to the red line. So how do we get the slope of the tangent line? We compute the limits. So this is a limit. T goes to t0, okay? Because the second point now is moving. When it's moving, so t0, t1 is like a fixed point. When it's moving, then is a variable, right? It varies. So let's call it t. So that's the limit when the second point t goes to the first point t0, m secant. So what's m secant? Change of s over change of t. So s of t minus s of t0 over t minus t0. So now this is the slope of the tangent line. So that's why the limits come into play. Okay, so we will talk about this more in chapter 3. So we will talk about this more in chapter 3. But this is the place why we need limits. Okay, definition, limits of a function. Suppose the function f is defined for all x near a, except possibly at a. If f of x is arbitrarily close to L, as close to L as we like, for all the x sufficiently close but not equal to a, we write the limit x goes to a, f of x equals L. So if I draw a picture here, okay, what does the picture look like? Let's say this is 1, let's say this is 2. Okay, so this is the f. Okay, you can see when x is getting close to 1, okay, when x is getting close to 1, we go. The y is getting close to 2, right? And also if we are here, when x getting close to 1, our y is getting close to 2. However, the function does not have to be defined at 1. Maybe that point is missing. That's why you can see, I put an open circle right there. Because, the limits, you just want to know the situation near the point, but not exactly at that point. So you don't require to know any information at that point. So we mark the limit of f of x as h approaches a equals L, this doesn't mean that f of a is L, and f of x does not have to be defined at a. So, for example, I can draw this picture, okay, let's look at this picture. This case, what does that mean? Well, the limit x goes to 1, f of x, well, that means, when you're near 1, you go. You see, your y is getting close to 1. However, your f of 1 is, so right at f of 1, okay? What, y at x equals to 1, you can see, here we have an open circle, but here we have a solid circle, so f of 1 equals to 2. Okay, so, alright. Equals 2. So far, so good, everybody. And if we have this picture, then we have f of 1 is not defined, so undefined. Okay, so for the limits, we just need to know the information near that point, but not exactly that point. Okay, so let's look at example 1. Evaluate the limits x goes to 2 of x minus 2 over x squared minus 4, and the limits x goes to negative 2, x minus 2 over x squared minus 4. Okay, so what are the steps of computing limits? Okay, so first, here are the steps. It's very important that we write down the steps because this is calculus 1. You're gonna learn more and more math class, okay? And so this calculus 1 is like the foundation of many math courses, right? So it's very important to come up with the study skills. So I would suggest you to write down the steps for each kind of problem. It's like a recipe, right? So we write down the recipe, and then next time we know, if we want to solve this kind of problems, okay, we know what the steps are. Okay, so what is the step? So here we want to compute the limit. Okay, that's our goal. We want to compute the limit. And then what's the step? What's the first step? Well, the first step is we plug in the numbers. Okay, so let's look at the first one. So we have x goes to 2. So we try to plug in 2. But when we try to plug in 2, what happened? Well, 2 minus 2 over 2 squared minus 4. 2 minus 2 is 0. 2 squared is 4. 4 minus 4 is also 0. So what is 0 over 0? Okay, what does that mean? Okay, so if you get 0 over 0, go to step 2. Okay, so 0 over 0, my previous students, sometimes they think, 0 over 0, no solution. No, you always have a solution, okay? So 0 over 0 can be anything. So 0 over 0 can be a number, okay? So I can give you, for example, like a 2x over x, right? And so 2x over x, well, it's 0 over 0, but the x cancel, you get 2. So it could be a number. And it could be like x over x squared. So we also have 0 over 0. But however, in this case, we can cancel 1 over x. So we get 1 over x. Do you know what is 1 over x? Well, if your denominator is getting smaller, okay, let me ask you. What's 1 over 0.001? Oh, that is 1,000, right? So 1 over a very, very small number is gonna be a big number. But if this number is negative, it's just gonna be negative number, but the magnitude is bigger. So when x goes to 0 in the denominator, this guy will actually be plus or minus infinity. So be careful. We know, let me change your color and put it down here, because I know many of you will get confused. 1 over 0 isn't it undefined? Yeah, 1 over 0 is undefined, but the problem is we don't have exactly equal 0 in the denominator. We're approaching it from the right. So this notation means you're getting close to 0, but is smaller is positive. And this guy will give us it will give us positive infinity. How about 1 over 0 minus? It will give us negative infinity. Okay, 0 minus is a number getting close to 0, but it's negative. Okay, so far so good. So, that's why here it depends on whether x goes to 0 from the left, whether it's positive or whether it's negative. So our answer could be plus or minus infinity. Alright, let's continue. And we can also have limits x squared over x, right? This is 0 over 0, but you can cancel the x. Then we get x. Well, limit of x, when we plug in x is 0, we get 0. Oh, by the way, why we can cancel the x here? Because here, we're letting the limit x goes to 0, but x is not equal to 0. So that's why we can cancel the thing which is not equal to 0. Okay? So x not equal to 0. That is why we can cancel it. We're just taking the limits, x approaching it, but it's never equal to it. Okay. Let's continue. So, first step, if we get 0 over 0, you can see it could be a number, it could be infinity, it could be 0. So we have no clue what that is. So what we should do, if we get 0 over 0, that must be a bad guy. Okay? So there is a bad guy. What is a bad guy? The bad guy actually make the numerator and the denominator 0. So we have to figure out what the bad guy is. So if you see polynomial, okay, then factor it. Okay, so here we have actually more cases, but in the cases of polynomial, you factor it, and we also have some other cases. Okay, so here we can factor it. How do we factor it? Remember, don't forget you have to carry the limits in each step. So x minus 2 is already factored, but how can we factor x squared minus 4? Well, that is x plus 2, x minus 2. Why is that? Because we're using the formula a plus b, a minus b is a squared minus b squared. Okay, so for all these common algebra formulas, you guys need to memorize. Okay, it's very important. So those are the common ones we use. So far, so good, everybody? Alright, let's continue. Now, after we factor it, can you see the bad guy? Yes, x minus 2 is the bad guy because when x goes to 2, x minus 2 goes 0, right? It goes to 0. So this is the bad guy making the numerator and denominator 0. But now after we cancel it, what happened? Well, we are safe. So we can plug in 2 now. So 1 over 2 plus 2, which is 4. So we actually get a limit. And you can see, this is the graph of, this function. And when x goes to 2, this guy actually is 1/4. You can see, we have a limit 1/4, and then that's why here we have an open circle because for our domain, is x, the denominator cannot be 0, so x cannot be plus or minus 2. That's the domain. So in terms of the picture, we can see here we have an open circle at 2. Okay, everybody? And how about the second limit? Let me use a different color because a lot of green color, I want to make a difference. Okay, so I forgot to say. So the second step after we cancel the bad guy, then we are safe. We can plug in the numbers again. All right. And then next. Okay, so for this guy, when we try to plug in a number, what do we get? -2 minus 2, and then -2 squared minus 4. Well, -2 minus 2, oh, that is -4. And then our denominator is 4 minus 4 is 0. So actually, when we goes to 0, this is not exactly 0, is like getting close to 0, right? If you have a number over 0, so constants over 0 is gonna be positive infinity or negative infinity right here. Okay, so that's constants over 0 is going to be either positive infinity or negative infinity. So this is actually plus or minus infinity, depending on which side you're approaching -2. So if you're approaching it from the left, you can see this picture, we actually get a vertical asymptote here. So vertical asymptote. Okay, so when x goes to -2 from the left, we get x goes to minus infinity. Why is that? If you can think about that, if x goes to -2 from the left, so negative means from the left, because the left is more negative side, the right is more positive side, and then what happened? Well, your denominator is getting close to 0, but is 0 plus or 0 minus? Think about it. If we're going from the left, our magnitude is bigger than 2. Even though it's negative, but the magnitude is bigger than 2. So the x squared minus 4 is actually positive. So we have -4 over 0 plus is infinity, but how many negative signs are there? So we have now one negative sign. So that's why you see is a negative infinity. So the y will actually goes to negative infinity. Oops. So let me see. Can I move this a little bit? Okay. So then I can put my y goes to negative infinity. So when x goes to -2 from the right, then my y goes to, you see, when we go to -2 from the right, the magnitude is actually smaller, right? So x squared minus 4 is actually negative. So we have 0 minus there. And then what happened? Is infinity, but we have two negative signs, so it make it positive. So that is why here, when x goes to -2 from the right, our y goes to infinity. Okay, so if the limit is positive infinity or minus infinity, we say the limit does not exist. Okay, but in your homework or your exams, if you can use infinity to describe, please use infinity. Okay, so write your answer as infinity. All right, so let's continue. Let's look at example 2. So actually there are 3 ways to find the limits. One way is use the table. Second way is to plot the graph. Okay, and the third way is algebraically. So look at the formula of the function. Okay, so how do we get from the table? So you see x getting close to 0. So then we can plug in x is plus or minus 0.1, plus or minus 0.01. So getting you can see here we're getting closer to 0. And then when you plug in your calculator, so 1 over x squared. So 1 over 0.1 squared is 100, and then 1 over 0.01 squared is 10,000, right? You can see, oh, it's getting bigger. Then you can know that our limits is infinity, right? When x goes to 0, our limit y is infinity. And the second, we can see from the graph, when x goes to 0, oh, my y just goes up, right? It goes to infinity. So that's why the answer is infinity. And that's from the graph. And for the formula, what happened? Well, when x goes to 0, so you have 1 over 0, and it's 0 plus, because x squared is always positive. So 1 over 0 plus, we know that is also infinity. So there are 3 ways we can find the limits, but table 1, using the table or using the graph, we'll conjecture the limits. To rigorously prove what the limit is, we should use the formula. Okay, so in your exam, if they just ask you to evaluate the limits, then you're looking at the formula and you want to evaluate the limits. Okay, let's continue. So how about this function? Well, this function look more complicated. So x goes to 0. So that's why we also try to plug in 0.1, 0.01 and make it smaller. And then put those numbers. Okay, so we place x by 0.1 and plug into your calculator. And then what do you get? Well, this is the number you get. Can you see what the limit is? I would say this one. So that's 0.125, right? And from the graph, you can see as 0, we know it's undefined as 0 because the denominator cannot be 0, right? 0 is not in our domain. So we have an open circle right there. But you can see when x getting close to 0, go. Okay, the y is this value. What is that value? Well, this is 0.1, this is 0.2, well, then this is 0.15. This guy is like a halfway between 0.1 and 0.15. So that is 0.125. So far, so good. Okay, so we can see from the graph. And then, so next, from the formula. So how do we rigorously prove that the limit is 0.125? Okay, so here we follow the steps. Remember, we always follow the steps. First, we plug in a number, and if we get the number, that's good. If we get 0 over 0, it means there is a bad guy. So then we need to do something to it. Okay, so let's see. Okay, so let me copy down this function and then let's continue. So when x goes to 0, what happened? Well, then we have square root of 16, which is 4. 4 minus 4 is 0. Oh, we have 0 over 0. So that means there is a bad guy. Well, but so last example, we learned when we see a polynomial, we can factor it. But here, this is not a polynomial. We cannot factor it. What we should do is, well, this is the difference of square roots. So when you see difference of square roots, what do? You multiply by its conjugate. So what is the conjugate? Well, conjugate is we have the same terms, but the middle sign, flip it. So if it's negative, then now you flip it to positive. So this is the conjugate. When you multiply by something, you also need to divide by that thing, so you're not changing the function, right? So this is the conjugate. Now what happened? Why do we want to multiply by the conjugate? Well, because a plus b times a minus b is a squared minus b squared. Well, the square will actually help us to get rid of the square roots, right? So this is like our a, this is our b, this is our a, this is our b. So a squared becomes square root of x squared plus 16 squared minus b squared, which is 4 squared. And then the denominator is still there, so copy them. Okay, now what happened? So square and square root, now you can see they cancel. So we have x squared plus 16 minus 4 squared is 16. Oh, can you see we can cancel something? The 16 get canceled. Well, if the 16 get canceled, what happened? We only have x squared left. That is our bad guy because it make the numerator and denominator 0. So now we can cancel the bad guy. So we are safe. Well, by the way, when you cancel it, you get 1 on top. You don't get 0, okay? Okay, so when we plug in x is 0, we're safe now. So we can plug in x is 0. So square root of 16 is 4. So 4 plus 4 is 8. So our answer is 1 over 8. Do you know what is 1 over 8? It's actually 0.125. It's exactly what we get from the graph and from the table, right? So see, let's complete our steps. So here, when we see difference of square roots, okay, we multiply by the conjugate. Oops. Ran out of space. Okay, so when we see difference of square roots, we multiply by its conjugate. So multiply. Oops. Multiply by the conjugates. Okay, so you see one more line there because we're gonna see one more example later. Okay. All right. So how about this function? Well, that looks crazy, right? When x goes to, by the way, first of all, you know sine function looks like this, right? And cosine looks like this. So this is cosine, this is sine. It's oscillating between -1 and 1, right? And then here, when x goes to 0, well, pi over x actually goes to infinity, right? And sine of infinity is oscillating between -1 and 1. Is actually faster. So that's why you can see this crazy region. But it's bounded between -1 and 1, okay? And in this case, there's no way we can describe the limits because we don't get a number. It's changing. It's oscillating between -1 and 1. We don't approach to a number. So in this case, we say does not exist, okay? This is does not exist. And this is different than the case sometimes does not exist. We have infinity or minus infinity, but in those two ways we can still describe it, right? We can use infinity to describe it. We use minus infinity to describe it. It's still approaching to a direction is right positive infinity or negative infinity. But this case, however, there's no way we can describe it. It's oscillating between two numbers. Okay, so it's not going to a direction. So that's why in this case we can say does not exist. Okay, the limit does not exist. All right. Okay, so next, one-sided limits. Suppose f is defined for all x near a with x greater than a. Then f of x, if f of x is arbitrarily close to L for all x sufficiently close to a with x greater than a, then we write the limit x goes to a from the right-hand side. The right-hand side is more positive, so a plus. F of x equals L. We say the right-hand limit of f of x as x approaches a from the right equals L. So let me draw the picture. Let's say this is 1. And let's say this is the 2. Oh, maybe, okay, like that. Okay, then what is the right side of limits? You can see when x goes to 1 from the right, we're actually on this piece. So we have go. The y approaches 2. So in this case, x goes to 1 from the right, f of x equals 2. Okay, and On the other hand, what is the left side limit? When x goes to 1 from the negative, so negative is on the left side. So we're on this piece. See, we go. The y goes to 1. Okay, so this is the two-sided limits. And you can see f of 1 is actually not defined because we see both open circle there. Okay, so this is the one-sided limits. You can see the left-sided limits and the right-sided limits, they do not have to be equal. And important, if a limit exists, even only if both sides agree. So if the limits, okay, so if the limit equals L at A, well, that means the left side of the limits equals A and the right side of the limits equals, the left side of the limits equals L and the right side of the limits equals L as well. Okay, so this is so important. Next, we're gonna given the graph and we want to figure out all the limits. Okay, so this is the graph. Open circle means the point is missing. A solid circle means the point is right there. Okay, so what is the limit? X goes to 2 from the right. So where is 2? So that is the x value. So x value is right here. So we're looking at the 2 from the left or right. From the right, then we actually look at this piece, right? So we would like traveling, we go. What's the y value? 1. So that's why this is 1. So far, so good? And then, how about 2 negative? So that means x is going to 2 from the left. Then we're which piece? See, we're this piece. So y is go. My y value is 3. So this is 3. So far, so good? Okay. And how about the limit? X goes to 2. Well, goes to 2 because you see the left side limits and the right side limits, they do not agree. So this guy does not exist. Okay. So if the left side of the limits does not equal to the right side of the limits, then the limit at that point does not exist. How about x goes to 5 from the right? So from the right is right here. So we're at this piece. So go. Oh, that is my y value is 2. How about the left-sided limits? Well, we're here, we're go. So this piece, go. So my y is also 2. Well, then what is the limit? What is the limit at 5? Because the two-sided limit agrees and they both equal 2. So that's why this limit is 2. So far, so good, everybody. And furthermore, we can also ask that what is f of 2? Well, f of 2 is right here. Do you see any dots over there? No. So this guy is undefined. How about f of 5? Well, f of 5, do you see any dot there? Yeah, here. What is this dot? Okay. Let me suppose this is 1.2. Then this dots f of 5 is 1.2. So far, so good, everybody. All right. So I hope you have an idea like how to look at given the graph, how to use the graph to find the limit. All right. So let's continue. Okay, first of all, the limit, x goes to 0 from the right. So 0 is right here. We're approaching it from the right. Oh, what happened? You see, it's oscillating crazy. So in this case, what do we say about the limit? Yes, does not exist because it's oscillating between 0 and 2. So we're not approaching to a number or infinity or minus infinity. So we just say does not exist. How about x goes to 1 from the left? From the left is this piece. So my y is, we go here. That is 1. So far, so good? Yeah. So in the videos, I can actually draw on the graph so you can see how I think. So how about x goes to 1? Well, that is the two side limits. We might need to figure out we know what the left side limit. How about the right side limit? Well, the right side limit, we look at this piece, right? My y is getting close to 0. Do they agree? No. So this guy does not exist. Alright. And then how about the limit x goes to 2? Well, goes to 2, you see the left side limit and the right side limit, they actually agree. So they agree and equals 1. So we have that. How about x goes to 4 from the right? From the right is here. Oh, you can see it goes to positive infinity. Okay, so he answered positive infinity. How about x goes to 5 from the left? From the left, oh, you see right here. So it goes to minus infinity. So you can see we actually have so vertical asymptote at x equals to 4 and 5. So in the session 2.4, we will talk about more on vertical asymptotes. In session 2.5, we will talk about horizontal asymptotes. Okay, so what is f of 1? F of 1, right here, do we have a dot there? Yeah, this is a dot. It looks like this is 0.5. Okay, so we can answer 0.5. So this is 0.5. How about f of 2? Well, do you see any points at 2? No. So this guy is undefined. Okay, very, very important. For limits, if you don't have a value for it, you say it does not exist. For function, if you don't have a value for it, you say undefined. So don't mess up. So limits, we say does not exist. Okay, and the function value, we say undefined. Don't mess up. Okay, and do we have more parts? So yeah, f of 3. Where's f of 3? Oh, you see, because we don't have a open circle, it means the point is right there. Okay, if there's no open circle, it means the point is right there, is not removed. So, that is also 0.5. So this is 0.5 as well. So far, so good. So I have a student ask me, oh, I don't see a solid dot right here. So, but it's okay because we don't need a solid dot. This piece is connected, is continuous at that point. So it's smooth and, it's not smooth, but it's connected. So it means that point is not missing. So we don't need a solid dot to indicate that point is right there. As long as the piece is connected and it's not an open circle, that means the point is already, is not missing. It's right there. Okay, so f of 3 is 0.5. And that finished our session. So if you have any questions, feel free to email me. Cheers! Bye!